Hi everyone, this is Design and Application of Lasers, Phys 4250 or 8250 at the University of Windsor, and I'm your instructor, Dr. TJ Hammond. This week we'll be covering Chapter 3 in your textbook, Laser Physics, and this is Absorption, Emission, and Dispersion of Light. So for Monday's lecture, we're going to be covering absorption and dispersion. And why are we covering this material this week? So last week we discussed briefly where laser levels come from. So we saw that they can come from, in quantum mechanics, whenever we have these bound states, we'll always get these discrete energy levels in an atom. We can also get these discrete energy levels in a molecule for the electron excitation. And so we get these quantized energy states. We also found in molecules that there's also these vibrations, and that is those are also quantized, those are also discrete. We get these discrete energy level transitions, but those are more in the infrared, whereas the electronic transitions tend to be more in the either near infrared, visible, or slightly UV. We also looked at solids, so you can have bands due to the band structure of these periodic potentials in solids. And so we looked at how these kind of energy levels came from. This week we want to understand how the electron interacts with light, so we can see how this absorption and this emission can come about. Most of this is going to be discussed in a classical model. So these will be classical fields interacting with an electron in kind of a classical way. But for the grad students of this course who've probably seen some quantum mechanics before, I'll get you guys to read up on the quantum mechanical treatment of this and see that you actually get very similar answers, or in fact it's the same answer, but it's discussed in terms of discrete levels as opposed to a classical levels. So what we want to understand this week is how does light get absorbed, and what happens as this light passes through a material, so if it doesn't get absorbed. So the daily assignment this week is going to be reading and summarizing section 3.1, just the introduction of this. I'll be taking some of the notes of the next, following 5 or 6 pages in your textbook, but I'll be taking a lot of the notes actually from your electricity and magnetism textbook as well. So don't worry too much about the details, because I'll be working through the details using different references. Okay, so what is this electron oscillator model? So for those of you who have taken 3210 electromagnetic waves with me, we covered this in section 9.4 of Griffiths when we talked about absorption and dispersion. For some reason, your textbook doesn't actually talk about Maxwell's equations, although Maxwell's equations are extremely important when deriving this. Eventually, one of the topics for your final projects can be Maxwell block equations, but your textbook doesn't just introduce the ideas of Maxwell's equations when talking about propagation of electromagnetic radiation, which I found kind of strange. So I'll be kind of skipping some of the points, but we'll be needing to, but if you've taken electricity and magnetism with me, you can use some of those ideas that we've discussed in class on where these electromagnetic waves come from. Okay, but the upshot is that what we care about is the Lorentz force. Okay, and this is going to tell us how this electromagnetic field interacts with this charge, and so that's due to this Lorentz force. Okay, so this electromagnetic radiation is going to be these electromagnetic waves, and so these are given by this electric field and this magnetic field here. If you want to actually prove this, well, you actually need to recall Maxwell's equations in order to do this, to see why the electric field is, E naught cosine kz minus omega t, and it propagates in the z direction, but it's polarized in the x direction. it doesn't matter if it's polarized in the x or the y direction, but it's polarized orthogonally to the direction of propagation. And the magnetic field is also the same thing. It has the same phase, so it's also kz, cos of kz minus omega t, but it's polarized orthogonally to the electric field, and it is also polarized orthogonally to the direction of propagation. But notice this key thing here is that the magnitude of the magnetic field is 1 over c times the whatever you have for the electric field. And so the magnitude of that magnetic contribution in the Lorentz force law here is going to be a lot smaller. Okay? To actually show that, or to think about this a little bit more, it'll be one of your problems in the assignment on Friday. So basically, in order to prove this, you'd need to take 3210 with me, electromagnetic waves. But for now, you'll just have to take my word for it. But in summary, plane waves propagating in free space, they're not interacting with matter. Electromagnetic waves are polarized along the electric field. So when we talk about the polarization of light, we'll be talking about the polarization of the electric field. And that's because that electric field is 3 times 10 to the 8 times bigger than the magnetic field. The electric field is orthogonal to the magnetic field, and they're both orthogonal to the direction of propagation. And the magnetic field is in phase with the electric field, and as I said, but its amplitude is smaller. Okay. So why is that important? So we'll make the approximation here, instead of using the full Lorentz force, we'll make the approximation that this force of this electromagnetic force is just going to be approximately this charge, whatever the test charge is, times this electric field. Okay, so what we have is our electromagnetic wave here is propagating in the z direction. This is polarized in the x, and this is in the y. And this encounters some atom, okay? And so this atom has this nucleus here, and it has this electron here. So this electron is negative charge, and this nucleus is going to be some positive charge. And for this model, and this is why I say this is a classical model, is that this electron is just attached to this nucleus by some spring. Obviously, that's not really how it works. For those of you who are taking quantum mechanics, you know, this electron is bound by some, you know, in some orbital. But we're going to say that we disturb this electron perturbatively, and this perturbation will act like this electron is like it's oscillating on a spring. Okay, so this model obviously precedes quantum mechanics, but it actually works quite well. So we have this electron, it's negatively charged, it's now in this electromagnetic field. This electric field is proportional to this force, and so what we want to know is what the motion is of this electron. And so we put it in Newton's laws, and we say ma is equal to the total of the spring, the force of the spring, the force of damping, and this electromagnetic field. So the force of the spring is whatever, you know, that spring will depend on what this electron orbital is. It'll depend on this nucleus, you know, things like that. This damping, we don't know anything about this damping term yet. It's just going to be some kind of thing saying energy could possibly get absorbed in this system, and that'll be this damping term. We have no idea what it is. It's purely phenomenological right now. Eventually, you would need to know quantum mechanics to exactly understand what this damping constant is. But for now, we'll just say this is just some value. We have this electromagnetic force, FEM. So maybe the quality of this recording is deteriorating. Hold on just a second. Okay. So we have this spring model. So we have this force of the spring is negative kx. Of course, it's k is the spring constant. And of course, that force is going to be proportional to that distance from equilibrium. And we have this damping force, which, as I said, is just some phenomenological thing, and we're just going to call that gamma. And for convenience, we're going to have it multiplied by m, and we'll just have, since gamma is just a constant anyways. And this damping force is proportional to the velocity. And this is because when you're dealing with simple harmonic motion or damped harmonic oscillation from Phys 2500 in intermediate mechanics, we've seen this kind of problem before. So we set up the problem the exact same way as what you would see in intermediate mechanics. So we're going to also assume that the electron is going to oscillate in the same direction as this field, and so everything is going to be polarized in the same direction. So we're going to have, I guess these should technically all have little vectors on them because they're all polarized in the same direction. And so, but everything's moving in x, so we're just going to drop that. And so we end up with this second order differential equation here. Now, technically, as I said before, the electric field is a function of z and t, and that is E naught cos kz minus omega t. But you'll notice that in this equation, we just have that it's a function of t, it's not a function of z. And dropping that z dependence is called the dipole approximation. And you can see why that's the case. So k is 2 pi over lambda. Oh, I should point out that this is the spring constant k, and this is the wave vector k. So yes, and I make that note here. Note the wave vector k is not the same as the spring constant k. Your textbook might use a k sub s for it to be the spring constant k. Unfortunately, it's just, there are only so many constants that people use, and k seems to be a really common one. So we have a spring constant k and a wave vector k. But the wave vector k is 2 pi over lambda. So lambda is going to be on the order of a micron, or 10 to the minus 6 meters, right? So k is on the order of 2 pi over 10 to the minus 6 meters. It's going to be something like 6 million inverse meters. Right? Now, if you think about this, what's the size of a nucleus? Well, this is the Bohr atom is about half an angstrom, right? So if it's half an angstrom, you can think about the difference in size that you have the size of the atom, call this the Bohr radius. The Bohr radius is much, much less than the wavelength. And using that approximation is called the dipole approximation. And so by dropping that, that Z dependence, we're going to say because this atom is so small, there's not going to be any Z dependence. This atom is going to see the same field across the entire atom or molecule or whatever, and so there's going to be no Z dependence, and that's called the dipole approximation. Okay, so what we get is this, in this dipole approximation, we get the second order differential equation where we have x double dot is going to be proportional to this spring constant, this damping force, and this driving force from our electromagnetic wave. So now it's a little bit easier if instead of talking about this as a real function, we can actually talk about this as a complex function. So complex functions will end up having the same solution because we just have the complex plus its complex, or sorry, the function plus its complex conjugate gives us the same as the real function. So it turns out to be just easier for the math if we think about this in terms of just the complex equation. So what we get instead of that cos term is our driving term is e to the minus I omega t. And so that's equivalent to saying that this cos kz minus omega t is equal to the real part of e to the I kz minus omega t, right? So we've just made that approximation or that assumption that we can use this as a complex driving field. And this will be really common in this course, and so we'll often be using complex driving fields. The field, as you know, fields are forces are always real, so the fields always have to be real, but we'll often use this notation of a complex field simply because the math ends up being a lot easier. And then when we get to the end, we'll say, oh, does this have to be real? Then we can, if it has to be real, then we can take the real part, or take the addition of the value plus its complex conjugate, and that'll also give us a real value. So in any case, we have this inhomogeneous differential equation. It's inhomogeneous because I hopefully have stressed this enough to you guys, because I think all of you have taken courses with me before, that this part on the right-hand side is not equal to 0. So everything on the left-hand side is our second order differential equation, and then we have this driving term on the right. And so if that were equal to 0, then that's our homogeneous differential equation, and this would be the same thing as if we just had like a damped harmonic oscillator, right? And so we'd start off at some initial amplitude, and this thing would just damp away. But instead, we have something non-zero on the right, so this is an inhomogeneous differential equation. And inhomogeneous differential equations have some kind of driving term. There's some kind of energy source. And so it's easy to write it as the differential equation part goes on the left-hand side, and then that driving term goes on the right-hand side. Okay, so plotting the solution to this will be your assignment, also the other assignment problem on Friday. Now, we'll understanding the transient parts and understanding the numerical solution to that. So for this lecture, what we're going to be talking about is the steady state solution. So in the steady state, we can make the approximation that x of t is equal to x naught e to the minus I omega t. And so what we're saying is that in some really, really long time in the steady state, that this system isn't evolving anymore. So it's now completely following this field, or it's completely driven by this field. There's no transient effects of what this electron had been doing before, if it was sitting there or doing something else. So that's what I mean by being in the steady state. So we take x of t in the steady state is going to be some amplitude, and then it's going to be e to the I omega t. Okay, we don't know what x naught is yet. In fact, x naught could be complex, which it will have to be, since we have x of t. We know that x of t is a position. It should be real, but we have e to the minus I omega t, and so that's obviously complex. And so x naught will also be some kind of complex value. So that means it could have a phase. It could have some kind of discrepancy. It doesn't have to be purely real, so it's not necessarily going to be some value of like 1 nanometer or something like that. Okay, then we take the derivative of that to get x dot. So taking the derivative of e to the minus omega t gives us negative I omega x naught e to the minus I omega t equals minus I omega x of t, and x double dot, so the second derivative, of course, because that's what we're solving for the second order differential equation, is going to be negative omega squared x of t. So we substitute all those values in, and we get minus omega naught squared x naught e to the minus I omega naught, or I omega t, minus I omega gamma x naught e to the minus I omega t, plus omega naught squared x naught e to the minus I omega t equals minus e over m e naught e to the minus I omega t. Now, you'll notice that everything is multiplied by e to the minus I omega t, so we can cross all those out and solve for x naught. Oh, and I should point out that the Lorentz force is Q times the electric field, but of course the Q that we care about is the electric charge. So as I mentioned in the previous lecture, for some reason the electron, which is what deals with current and everything, due to Franklin, he gave it a negative sign, and so now that's carried through until the present day. So the electric charge is negative, and so this always has a negative. Okay, so now we're solving for x naught. I'll let you do the math. It's not particularly difficult. And we want to solve for the steady state solution x naught. Here I follow the notation from Griffiths. We have this complex value. So as I said, x naught can be complex. And so since it's going to be complex, I'll give this little tilde here, just to remind ourselves that this thing is complex. And so what we get is x naught is negative E over m times E naught. So that's dependent on the electric field. Oh, and the screen quality might have gone bad. I'm not sure if this stays poor for the recording, but let me just give it a minute. Okay. All right, good. All right, we're back. This is just going to be my last slide anyways for today's lecture. So we solve the steady state solution for x of t, or x naught. And so we get negative E over m E naught. And then we have a denominator of omega naught squared minus omega minus I gamma omega. And so this is obviously complex because we have an I here. So what does this mean? It means that the amplitude of this electron oscillating, to some value x naught, this amplitude is proportional to the electric charge. It's inversely proportional to its mass. So this is really light. So what this is also telling us is that we could also do this for the nucleus, because the nucleus is positively charged and this guy is negatively charged. This thing could also be moving, but it's going to be moving a tiny, tiny, tiny amount to, say, we'll call this x naught prime. But this x naught prime is going to be much less than x naught, and that's because it's going to be 1 over the mass of the nucleus, as opposed to x naught is proportional to 1 over the mass of the electron. So for the hydrogen atom, that's 2,000 times smaller. For xenon, that's going to be something like 120 times 2,000, which is 100,000 times smaller or something like that. That's why we don't count the movement of the nucleus, because it's just so much smaller. Okay, so everything we deal with is going to be the electron. So it's inversely proportional to the mass of this charged particle, so that's the mass of the electron. It's also proportional to the electric field, so that's not surprising. We drive this we have a really strong electric field. This electron is going to oscillate a lot. And then we have this denominator. So we have this omega naught minus omega, or omega naught squared minus omega. And then we have this minus I gamma omega. So gamma is this damping factor, remember? So if we set gamma to 0, we have this omega naught squared minus omega squared denominator. So if we're on resonance, so if omega naught equals omega, then this x naught blows up. It goes to infinity. Okay? So if we have no damping, if gamma is equal to 0, and if we've tuned our laser frequency omega right to this omega naught squared, which, if you remember, omega naught squared is this ks over m, then if we're right on this resonance, then this amplitude of this electron becomes enormous, and this thing gets really, really big, and this thing moves around a lot, okay? But we have this damping term gamma that we don't know what it is yet. It's just phenomenological, but that's going to give this thing, it's going to prevent this thing from ever blowing up to infinity. It'll keep it some finite value. Now, because this denominator is complex, we want to make that denominator real, so we multiply it by its complex conjugate. And what we get out is two terms, where one term is in phase, and by saying in phase, I mean it goes e to the minus I omega t, and we get a second term that's out of, or pi by 2 out of phase, and that's because it's e to the minus I omega t plus pi by 2, and that's because of this I here. Okay, so that's it for this recording, and we'll be talking a little bit more about this in class, but for Wednesday's lecture, we'll discuss further absorption and dispersion.